Okay, let's move on to a next type of significance test, which is called the student's t-test. Okay, t-test. And this t-test is used for comparing means or averages. Okay, so if we want to test whether an average of some sample had some specific value or not, we set up a hypothesis that this average is equal to some constant value and apply t-test. As the name suggests, it uses the t-distribution, student's t-distribution. Okay, so suppose we have samples x1, x2 up to xn, and these are generated from some random numbers as random variables with mean mu and variance sigma squared. Okay, we here we are not assuming that these x1, x2, etc. follow the normal distribution. It may not be normal distribution. We are just assuming that they have the same mean and the same variance. Okay, and we want to test whether this mu, the mean, is equal to some particular value, mu naught, mu 0. Okay, so to test that, of course, this true value of mu is unknown. Okay, so we have to estimate from the data. The data are here. So we calculate this x bar as 1 over n times the sum over all these samples. Okay. Then, when this n is large, this will follow a normal distribution. Normal distribution with some mean and some variance. Okay, remember what kind of distribution this was? So what we want to test is that whether this follows a normal distribution with mean mu 0 and variance of sigma squared is the variance of each of these variables, and if we take this, define this, the variance would be sigma squared over n, right? So this was according to the central limit theorem. Central limit theorem. Okay. So we are not assuming any distribution for each of these samples, but when the number of samples is large enough, then x bar will follow this normal distribution. That's the result of the central limit theorem. Okay, so if we normalize, standardize this x bar, let's define this x bar minus mu 0 and sigma over n square root of n. Okay, then this will follow the standard normal distribution, right? So this sigma over square root of n is the standard deviation obtained from here. Okay, so if our hypothesis this is correct, then this will follow. Okay, then if this x bar actually deviates from mu 0 by a large amount, then that probability will be very small and we can reject our hypothesis. Okay. But all these arguments assumes that we know the value of sigma. Otherwise we cannot look up the table of normal distribution, right? But in reality, we may not know the value of sigma. So somehow we want to get rid of it. And one way to do is to introduce the T statistic. Remember? So if we define the sum of square deviation from the sample mean, okay, then as we have learned before, this s squared over sigma squared follows the chi-square distribution, okay, of how many degrees of freedom? There are n terms here. In that case, we have n minus 1 degrees of freedom. Okay, so we define small s squared as large S squared divided by n minus 1. So this is the number of this is the degrees of freedom of this chi-square distribution. Then then we define the t random variable, x bar minus mu over small s over square root of n. Okay. Do you remember how we got this? We have this. Okay, let's take this. Okay, on one hand, we have this, which follows the standard normal distribution. Okay. On the other hand, we have this, which follows the chi-square distribution. Okay. So if we remember, okay, so d over square root of s squared, so this is chi-square variate, and all divided by the number of degrees of freedom, we will have x bar minus mu naught and sigma square root of n, and this large S squared divided by n minus 1 is small s squared, and if we take the square root, we have small s out, and we have let's see, sigma out, and this sigma will cancel. So we have x bar minus mu naught, and we have this square root of n, move this to here, and we have s over square root of n. And this follows the t distribution with how many degrees of freedom? That's here. So n minus 1 degrees of freedom. Okay. So in this expression, we don't have the unknown sigma anymore. So x bar can be calculated purely from the data, and the small s can be calculated purely from the data, and n is of course the number of data. So, and this mu naught is our given parameter for the hypothesis, so it should be given. So there are nothing unknown here, and we can just apply the t distribution to this, and if the probability that this t-variate has a certain value or more is small enough, then we can reject our hypothesis that the mu is same as mu naught. So this was hypothesis. If the probability of this is small enough, then we reject this. Otherwise, we just don't reject. Okay. Okay, let's look at an example of t-test. So here are some results of some drugs, hyoscyamine and hyoscine, hyoscyamine, hyoscine, and basically they are supposed to be sleeping drugs, okay, sleeping pills. So they are expected to improve sleep, okay. So that property is called what is it? Soporific. That's a difficult word. Soporific. So basically, I think this means improve sleep. Okay, so we have two types of drugs, and we have 10 patients. So if patient 1 takes hyoscyamine, then his sleep was improved by 0.7 hours. Okay, he slept longer. And patient 2, when taking this hyoscyamine, his sleep actually decreased by 1.6 hours, and so on. So we have this data. And we have similar data for another drug, hyoscine, like this. And first, let's look at hyoscyamine only. Okay, so let's look at this part. And if we calculate the sample average, we should have plus 0.75. Okay, so we add all these and divide by 10, we have this. Okay, and small s, remember the definition? So first we calculate the sum. So there are 10 patients. Sum of square deviation from the sample mean. Okay, this is the sample mean here, and xi is each of these data. So this is the sum of square deviation from the sample mean. Okay, and there are 10 data points. So small s squared is defined as large s squared divided by n minus 1, which is 9. Okay, in this case. So if you do this and take the square root, you should have 1.79 here. So using this, you calculate the T statistic by this. Okay, divide this, divide this. Divide this value by this value divided by square root of 10. Okay, don't confuse this 10. Okay, this 10 is the number of samples, but here when you calculate this s, you divide by n minus 1, so that's 9 in this case. Okay, anyway, so we have, after all these calculations, we have this T statistic for hyoscyamine. Okay, so this is a T distribution with 9 degrees of freedom. Okay, 9 degrees of freedom. 9 degrees of freedom. So, is this significantly large? So let's look at the table of T distribution. So this is the table of T distribution, and since we have 9 degrees of freedom, okay, we look at this row. Okay, so in this case, these numbers show the probability of uh, T statistic less than this number. Okay, let's see. So if we want to test by, let's say, 5% significance level, we look at this one, 0.95. Okay, so this means this area will cover the 95% of the area under the curve. So that means the remaining region, okay, the remaining region here is only 5%. Okay, so let's look at this column, and we have this number, that's 1.833. So what was our statistic? 1.32, which is less than that number, okay, 1.833. So this drug, hyoscyamine, is not significantly improving the sleep of the patients. Okay, based on 5% significance level. Okay, so look at the other drug, hyoscine, and if we calculate the same things, x bar, s, and t statistic, we have this value, 3.68. So this is clearly larger than this value, 1.833. So this hyoscine improves sleep significantly by 1%, 5% significance level. What about 1%? Okay, if you want to check 1% significance level, you look at this column. That's 2.821. So our statistic here is still greater than that. So this hyoscine is effective with 1% significance level. Okay. Now, uh, instead of looking at each drug separately, let's focus on the difference. Okay, so the difference here means hyoscine minus hyoscyamine. Okay, so 1.9 minus 0.7 is 1.2, and 0.8 minus 1.6 is plus 2.4, and so on. So for these values, we again calculate the sample mean and small s. So this is if you remember, this is unbiased sample standard deviation. Okay, and after all, the t statistic becomes 0.406, which is clearly larger than the 1% significance level of 2.86. So actually, it's quite large. So it's what, 4.06. So it's greater than this one. So what's this? 0.25% significance level. Wow, it's really effective compared to the other drug. So that's how you use t-test. Now let's consider another use of the t-test. Suppose we have two sets of data, two sets of samples, x1, x2, up to xm, and y1, y2, up to yn. So the number of data points are different in these two sets. Okay, so and these first data set are generated from a random variable with mean, let's say, mu x. And the second one should have its theoretical mean mu y. Okay. And we assume they both have the same variance, okay, sigma squared, sigma squared. Now, we want to test whether the two means are the same, okay? So this is the question. This is our null hypothesis, okay? Okay, so, and we can apply the t-test to this problem. Okay, to do so, first we calculate this first sum of squared deviation from the sample mean in the first sample. So 1 to m xi minus x bar. Of course, x bar is the sample mean. It's a simple sample mean. And S2 squared, the sum from 1 to n y bar squared, and of course y bar is the sample mean of the second sample. Okay, now we combine these two. So s squared is s1 squared plus s2 squared. And from this large S, we define small s by dividing by m plus n minus 1. No, it's minus 2 in this case. Now, at this point, you are forgiven not to understand why this is m plus n minus 2. And this number can be derived in a similar manner as we have derived the unbiased sample. We just combine these two and find some orthogonal transformation, right? So in this way, we define this S, and we define the T statistic as x bar minus y bar divided by S times, okay, this is not divided by, okay, it's S times square root of 1 over m plus 1 over n. Okay, so this is a little bit complicated. But anyway, if you have two samples and want to compare the means, here's how you do. Okay, calculate the sum of squared deviation from the sample means and add them, divide by, this will be m plus n minus 2 would be the degrees of freedom. Degrees of freedom. Okay, so this will follow the t distribution with m plus n minus 2 degrees of freedom. Okay, and I will omit the example. Yeah, you can just mechanically apply this technique. Well, maybe you should have some example. Okay, here's one. So this is Fisher's example. Okay, Fisher is one of the founding fathers of modern statistics. Okay, and he was actually a biogeneticist. Okay, so he was in a farm studying plants or some insects maybe. Anyway, so 8 pots growing 3 barley plants each were exposed to the action of high tension discharge, while 9 similar pots were enclosed in a earthed wire cage. So there are different sets of plant samples. Okay, and the number of shoots in each pot were as follows. Okay, so electrified group had this many shoots in each pot, and wire cage, earth wire cage, group had this many shoots in each pot. So if you calculate the sample means of these two groups, and are they significantly different? So you add them and divide by the number of samples, 1, 2, 3, 4, 5, 6, 7, 8. Then you get the sample mean, right? X bar. And you add them and divide by 1, 2, 3, 4, 5, 6, 7, 8, 9. Then you get the sample mean. Okay. And we want to test our hypothesis that X bar is equal to Y bar. Okay. To do so, we calculate the T statistic. So we calculate S1 squared by adding the squared deviation from the sample mean of all these, and we calculate S2 squared, so square deviation, sum of square deviation from the sample mean of all these sample. Then add them, so S squared, S1 squared, S2 squared, and divide by, so define small s, divide s squared by, so 8 plus 9 minus 2. So you define this, so s squared, what is it? It's 15. So then you can define the T statistic, you combining all these data. Okay, X bar, Y bar, what was it? S and square root of 1 over 8 plus 1 over 9. Then this follows the T distribution with 15 degrees of freedom. Okay. Then I don't know these values, so you should calculate them and look up the table. Let's see. In this case, we have 15 degrees of freedom. So let's look at this row. And for example, if we want to test, actually, test only one part, one side of it, then you can just look at this. For example, in case of 5% significance level, you can check this. So this number, 1.753. So in this case, we are actually testing whether X bar is significantly larger than Y bar. Okay, but what if we don't care about the order, which one is larger or smaller, right? So X bar is significantly larger or significantly lower, we don't care. In that case, we want to calculate not only one side but two sides. Okay, this red region plus this blue region. Okay, but T distribution is symmetric around 0. Okay, so around 0 it's symmetric. So if we want the sum of these shaded regions, okay, the sum of shaded regions to be in total 5%. Okay, this plus this to be 5%. Then we look for the significance level of 2.5% for the upper part. Okay, the lower part will be automatically 2.5% because of the symmetry. Okay, so in that case, we look at instead of 0.95, we look at 0.975. So we want to look at this value. Okay, and also we calculate not this but absolute value of this. Okay, so just ignore the sign. Okay, then we can check whether this is significantly different or not.